Hi, this is Robotorque Regression with Anant Kumar and Shreyas Kaliur. So we decided to split the problem into two parts. The first being finding the position of the bolt. To solve this problem, we were given a depth image as shown on the left and a grayscale image on the right. That gave a 3D representation of the bolt in terms of the distance of visible points on the bolt to a 2D plane, which was referred to as a camera. So basically, think of it like a camera taking a picture of the bolt and be able to calculate the depth to all visible points to that. So our approach was to use these positions to find a plane that intersects the most of these points, since this would correspond to the head of the bolt, since all of the other parts of it were sort of rounded off. The one part that was just a plane or just a flat surface was the head. We used a function that would test 1,000 planes defined by 3 random points, since 3 points define a plane, and return the plane that contained the most points within a given tolerance to make sure that any sort of error done by the camera would be taken into account. Finding the plane allowed us to calculate a normal vector of the plane, thus find the angle of rotation, since finding the equation of a plane pretty much just gives you the equation of the normal vector right there. So to find the center of the head of the bolt, we used a subset of original points that corresponded to the points on the head to calculate the center. So basically think of the red dots on the previous image. So taking the arithmetic mean of the points with a subset led to a skew in our center, since bolts oriented away from the camera would have more points near the camera than away due to the distortion effect, since as an image is tilted away from a camera, you can kind of see more points closer to it than further away from it. So instead, we found the average of the min and max x, y, and z coordinates and tried to use that, since the circular nature of the bolt meant this average corresponds to the center of the bolt's head. And then we compared it to the center of a bounding box that bounded all the points within the plane, just to see which one gave more accurate results. So the second part of the problem was to create the best path of the robot arm to move following the bolt as it moves. Our approach was to use different regression analysis tools and formulas until we found one that would best follow the bolt's movement. So we considered many methods of extrapolation, including linear, quadratic, and cubic estimations of the function. The movement of the bolt also seemed to oscillate, so we tried methods that would try to predict these oscillations. However, since the oscillations would often exceed the maximum distance the robot could travel in a time frame, we instead decided to smooth the data when extrapolating, so averaging data to get rid of sort of those oscillations and aim for the average bolt position as it moved through time. In the end, we used the cubic regression of the smooth data to base our robot movements. Finally, when combining parts 1 and 2, a problem that arose was that if the oscillations of the bolts are too large, the bolts might not appear in the image that the robot head takes. So if it moves maybe a size of greater than 30 or 40 away from the points that the robot can move to. So to account for these edge cases, we just had the robot continue moving in the direction of the previous position it was trying to get to, since the bolt would obviously be in that direction. And then in most cases, this let the robot eventually catch back up to the bolt and continue to track it.